Hey guys, in this video we are going to look at an example where we are going to find a marginal density function. And so in this case we are looking at a jointly continuous random variables. Right. So here, we're just going to start with a joint density function defined in this manner, right? So this is the way we are defining our joint density function. So our joint density is going to be 2 times y1 whenever our value of y1 is between 0 and 1, and also our value of y2 is between 0 and 1. And if it is if the values of y1 or y2 are anything else, then this joint density function is going to be defined to be equal to 0. So we're going to first sketch what this thing looks like. Again, my drawing, not fantastic, but we're going to do what we can. All right, so our values for y1 could be anything from 0 to 1. Right, so our value for y1 could be anything from 0 to 1. For y2, our value could be also anything from 0 to 1. We don't have our value for y2 being bounded by y1 or anything like we've had in some of the previous videos. So you have kind of like that square down there at the bottom is like a shadow of the surface that we're going to be looking at. Now, what is the function height? The function height is going to be above that square. You should be looking at 2 times whatever the value of y1 is. Right? So when our value of y1 is 1, then our value of y2, our value for the density function should be 2. So 2 times that value of 1. So that's going to be no matter what choice of y1, so as long as the value of y1 is equal to 1, and the value of y2 is not bigger than 1 or less than 0. Right? So we have that, and there, that's going to hold no matter what. So we kind of have like this wedge shape. So it's not coming down to a single point, but it's going down to that line along where y1 would be equal to 0. And yeah, so that's what our density function looks like. It is that plane that's the top, so not that whole wedge shape. The volume of that should give us should have a volume of 1, a total volume of 1, because that's what matches up with probabilities. All right, so now let's find the marginal density functions for y1 and y2. So first, our marginal density function for y1. Our marginal density function for y1, we integrate over all values of y2, and our values of y2 are only going from 0 to 1, and we are integrating our function to y1, and we are integrating that with respect to y2. So when we integrate that with respect to y2, we get 2y1, y2, with our values of y2 being evaluated from 0 to 1. And so our density function is 2y1. Now, I say it's 2y1. Actually, our density function is our marginal density function for y1 is 2y1, provided that the value of y1 is between 0 and 1. And it is 0 otherwise. To find that marginal density function for y2, we're going to do the same thing, just different, right? So we're going to take and integrate over all values of y1, and so our values of y1 are going from 0 to 1. We're integrating our density function this time with respect to y1. And so when we integrate that with respect to y1, we'll get y1 squared evaluated from 0 to 1. And so we get an output that is just 1. So that's kind of the function, that marginal density function for y2. So we should be a little bit careful. So it's 1 provided our value of y2 is between 0 and 1, and it's 0 otherwise. So that is our joint density function. From this joint density function, these are the two marginal density functions for both y1 and y2. Right? And they match up with our definition from before. Right? So that's how, so we integrate over all choices of either y2 or y1. All right. So next time, in the next video, we're going to take a look at conditional probability functions, and then, yeah, we'll talk to you guys later.